Greetings everyone, I'm Yikun Mei. Today, I'm glad to present our latest work on massive access in extra-large-scale MIMO with mixed ADC over near-field channels. The presentation is structured into 4 sections. Let's begin with the background. The transition from 5G to 6G has ushered in a new era, introducing novel scenarios and extending the scope of 5G applications to include immersive communication, massive communication, and hyper-reliable and low-latency communication. As the 5G network approaches the performance limits, the 6G network sets forth new performance metrics on rate, connectivity, latency, reliability, and intelligence, etc. Achieving the ultimate 6G experience hinges on embracing cutting-edge technologies, and one of the pivotal contenders is the extra-large-scale arrays. Our work focused on the massive connectivity of 6G, which can accommodate a vast number of access devices, while only a few are active at a time. Furthermore, it extends the range of low data rates and occasionally necessitates high throughput. Additionally, stricter demands on latency is further required. Therefore, adopting the grant-free non-orthogonal multiple access protocol with the extra-large-scale array is a potential candidate to realize the vision of 6G. However, the challenges of deploying the extra-large-scale array are worthy of attention. First, the high power consumption and high hardware cost arising from the proliferation of antennas should be addressed to achieve a low-power, cost-effective extra-large-scale array. Then, as the array aperture increases, the devices may locate in the near-field electromagnetic propagation environments, which poses challenges to the acquisition of near-field channel state information. Furthermore, designing low-complexity detection algorithms at the receivers is also critical and essential. In this context, we proposed a grant-free random access scheme for massive connectivity based on the extra-large-scale MIMO system employing the mixed ADC architecture. Now, let's delve into the system model. As depicted in the figure, we consider a typical scenario of massive connectivity in the uplink for 6G. The base station employs an extra-large-scale array, considering a uniform linear array, while the device equip a single antenna. Our goal is to estimate the channel, denoted as H, according to the known received signal Y and the pilot matrix S, and currently determine which of the K potential devices are active. Due to the sporadic traffic of massive connectivity, the access channel H exhibits sparsity, allowing us to reconstruct it by the compressive sensing algorithm. Nevertheless, the extra-large-scale array aperture of the base station effectively increases the Rayleigh distance, leading to more devices located in near-field propagation environments. Therefore, it's imperative to account for spherical wave propagation in near-field channel modeling, where the distance from the device antenna to each receiving antenna is different. Consequently, the channel from the K device to the N antenna of the base station can be expressed as follows. Furthermore, the spherical wavefronts destroy the Fourier transform relationship between the spatial domain channel and the angular domain channel that exists for far-field propagation, leading to significant energy dispersion, as shown in the figure. It can be seen the far-field channel is sparse while the near-field channel suffers from energy spread. As a consequence, it is necessary to develop dedicated massive access approaches for near-field XL MIMO systems. On the other hand, to reduce the hardware cost and power consumption associated with extra-large-scale arrays, we consider the mixed ADC architecture for the receiver, which employs a combination of a few high-precision ADCs and a plethora of low-precision ADCs. The signal amplitude is adjusted through variable gain amplifiers before quantization. The quantized received signal is described as follows, where the low-resolution ADC is formulated as B-bit quantization. Simulation results validate that even a small number of high-precision signals can effectively enhance system performance. Then comes our proposed method. To accomplish joint activity detection and channel estimation, we proposed a 2-stage orthogonal approximate message passing algorithm, of which the block diagram is depicted below. Stage 1 involves dequantization and spatial domain-based activity detection. Leveraging a small number of high-resolution signals facilitates the expectation maximization algorithm for parameter estimation, and exploiting the common sparsity structure in the spatial domain enhances activity detection accuracy. Stage 2 employs the output from the first stage, including dequantized equivalent observations and detected support sets, to estimate the channel. To mitigate the energy dispersion, we divided the extra large-scale array into several subarrays. Within each subarray, the traditional dictionary is used to exploit the cluster sparsity structure to enhance estimation performance. In Stage 1, low-precision signals are dequantized by an element-wise MMSE estimator. After transforming the originally nonlinear quantized signals into a classical standard linear model, we can employ the orthogonal approximate message passing algorithm to detect the support set. Steps in detail can be found in our paper. The objective of Stage 2 is to estimate the piecewise angle domain channel after dividing, which is given as follows. Here, D represents the traditional dictionary matrix for the far-field channel. Then, based on the output of Stage 1 and corresponding initializations, we can estimate the piecewise angle domain channel using an equivalent observation model. For more detailed steps, please refer to our paper. Finally, let's move to the simulation results. To avoid the effects of large-scale fading, we assume the adaptive power control, where PT is the same for all devices. The performance metrics are the active error rate, AER, and the normalized mean square error, NMSE, in channel estimation. Essential simulation parameters are listed in the table below. We consider 512 antennas, 10% active devices, 2 subarrays, 2-bit quantization, and the distance range is approximately 10 to 100 meters, with a high-precision ADC ratio of 1/32. The baseline algorithms include the SWOMP algorithm estimating the spatial domain channel, as well as 2 AMP-type algorithms that consider dequantization and estimation of the angle domain channel. It can be seen that our proposed TSOMP algorithm exhibits a clear advantage in AER and NMSE. Next, we have validated the superiority of the mixed-ADC architecture and subarray-wise processing. The left graph illustrates the gains from individually employing the mixed-ADC architecture and subarray-wise processing. In the right graph, the element number of each subarray is fixed as 256. It shows that the benefits from subarray-wise processing are proportional to antenna array size. Lastly, we conducted simulations to evaluate the impact of the number of high-precision ADCs on system performance. A quantity of 0 indicates full low-precision ADCs, while a quantity of 512 represents full high-precision ADCs. Compared to using full low-precision ADCs, our proposed algorithm enhances the detection performance by employing the mixed-ADC architecture. As the number of high-precision ADCs increases, the performance steadily improves, aligning with our expectations. In conclusion, we proposed a 2-stage orthogonal approximate message passing algorithm for massive connectivity based on mixed-ADC extra-large-scale MIMO system over near-field channels. The activity detection relied on the common support structure of spatial domain channels and the accurate hyperparameter estimation from high-precision measurements. The piecewise angular domain channel was estimated by exploiting the cluster sparsity structure, where the near-field effect of the XL MIMO channels was mitigated by subarray-wise processing. Thanks for your attention.